So, to jump right in here, there are a lot of new devices that are very small, and they're made using a method called photolithography, which means to write with light. I worked as an intern at the WNF, which is the Washington Nanofabrication Facility. It's in the UW in Seattle. I did 2 internships there. I dressed like this, protecting all parts of my body from chemicals, and so I don't bring particles in. It's called a Class 5 clean room, which uses HEPA filters to make all the particles go away so they don't contaminate the devices that you're making and the projects you're doing. So today I want to discuss with you what devices are made, what they do, and I'm going to talk about photolithography and how it's done. And I'm going to show you some cool things that are made with it, so stick with me to the end to see these cool things. What is the nanofabrication process? The word micro is also used because when these devices are put together, even if they're nano-sized in one scale, they can be micro-sized in the other scale. So like the length could be nano-sized, but the height could be micro-sized. To make this a little more clear, nano-sized means 10 to the negative 9 meters. So a nanometer is 0.000000001 meters. Okay, that's a big scale difference and it's hard to imagine. So picture this, you have an 8-inch silicon wafer, and what you're going to want to do is you can put material on that wafer, in this case silicon oxide. Then you're going to write with light to put a pattern onto that wafer. You're going to take whatever material you don't want on there off, and then inspect it, and in the end actually cut it up into little pieces, package it, and then test it. So let's moving on. Let's see here. I need to describe what MEMS is. That's micro electromechanical systems. It's hard to say. It's a tongue twister, actually. So this involves a lot of integrated parts. The electromechanical part is usually achieved by a piezoelectric material, which converts mechanical strain, I think, into electronic signals. So there are crystals that are used as piezoelectric material when put beside a circuit of a wire, for instance, that's feeding it energy. It can convert that into mechanical strain, or from mechanical strain, if it's being pushed or moved, it can convert that into energy. So it works both ways. There are a lot of devices this can enable, which include actuators, sensors, switches, or gates, diodes, transistors, resistors. Anything you can think of is being done with this technology. Anything in the electronic spectrum anyways. So MEMS is one part. It's like the arms and hands of the system, but integrated circuits is like the brains. So you have to have both. You have to make them separately. You have to connect those things. Sometimes these devices are stacked on each other, and they can be stacked up still on the micro scale, but they can be stacked like to this to what they look like buildings of a city stacked up together, and they can make some very complex devices that do a lot of things very fast. So let's look at some of these little devices, these individual devices like cantilevers. Cantilevers are like diving boards. That's what I think of them. I picture this as a swimming pool, and here's the diving board. But what it does is it vibrates, and the more it vibrates, it can transmit that signal down the line. And so cantilevers are useful at harnessing and storing energy, and then transmitting energy. Cantilevers are used as accelerometers. They're used in phones, tablets, and digital cameras because it can tell where it's moving, it can tell what's up and down, and it can tell whether the image is upside down, and then it can display it right side up for you. You may have used a digital camera and turned it and seen it just flip. Of course, phones do this, so you've all seen that. Anyway, yeah, these cantilevers on the right, I got a picture. Credits are in the notes. I'm only guessing, but I'm guessing it senses light because they call it an array sensor. But I'm actually not sure what this does. I found this on the internet, but that is a good example of a cantilever. And I'll tell you a little secret. You can't create this just with light. You can create these patterns here with light, and then you have to use wet chemistry to get underneath, and you have to break it away from the material and leave it very thin and uniform. So it's very difficult to make. The chemistry is dangerous, but we'll get to that in a next slide. So fun fact, cantilevers are also used in missile guidance systems and airplane guidance systems. All right. The next generation of CPUs are made with photolithography. Samsung announced its 10 nanometer process in 2013, and the 10 nanometers refers to the distance between features on the material. So if you're using light to create features in the material, how close can you make them together? Well, I think that this is referring to the half distance between them. So you got to double that. So 20 nanometers between objects. But in 2016, Intel announced the same thing. They went to 7 nanometers, and then this Taiwanese company, TSMC, developed a 2 nanometer process. And that is not just using regular photolithography. We'll get to what that might mean in a second, but there is advanced forms of photolithography using extreme UV light, but I just use UV light in general. So let's see what it looks like. Here's the machine itself. You can see to the side, here's the wafer case where it carries the 8-inch wafer all the way around. So 8 inches is the diameter. We use these little tongs to take the wafer out very carefully, move it into the machine and put the mask over it. I haven't told you what the mask is yet, but it covers the wafer so the light goes through the mask to get to the wafer, and that's how you make the patterns. You design the mask to have the patterns on it, and then you can put that pattern on any number of wafers after that. Just wash, rinse, repeat. So this machine uses a mercury xenon lamp to make UV light. It uses 3 main wavelengths of light, ranging from UV to the visible light spectrum. So I'm just going to give you a second to digest that for a second. What is photolithography? How is it done? Well, you grow an oxide layer on the silicon wafer. Naturally, this happens in the air, and it'll grow about 1 to 2 nanometer width layer or height. The layer has a height. But we can grow those to 100 or 500 nanometers if we want, or even more. We test it to make sure it's uniform, or there is a uniformity pattern that we save, and then it needs to be pretty uniform to work. So we spin the wafer at 500 and then 3000 RPM while injecting what's called a photopolymer onto the wafer. There are a lot of different kinds of photopolymer, and I think we used SU8, which is a negative photopolymer. We then bake that at 1 minute for 100 degrees, and then the wafer is ready to be placed in the photolithography machine. So to be clear, what I'm saying is this photosensitive polymer will be placed on top of the oxide layer, which is on top of the silicon layer, and that wafer is then baked so that it hardens enough to stay all in shape and usable. And then we put that in the machine, and then we write on it with light. The polymer takes the light and either breaks away. If it's a positive photopolymer, it breaks away in a process called polymeric scission. And if it's a negative photopolymer, it hardens. So that's actually on the next slide right here. I should show you this and go back. The light goes through the mask here, If it's a dark area, it doesn't go through. If it's a light area, it goes through. And so where it hits, if it's a positive photopolymer, where it hits can get washed away, leaving these remaining. Or if it's negative, where it hits will harden, and when you wash stuff away, it'll get rid of all the spaces in between. This is useful because then you can etch underneath. You can go through with chemicals and etch underneath, or you can etch through here, and then when you wash it all away, you're just left with the part that you etched away. What remains is the oxide layer in this case. You can do this with metal also, or you can use this oxide layer grooves to lay metal down in there. So you can literally just create circuits, lines, wires in these grooves that you create with light. And that's what we do. So I think I explained the rest, but afterwards we develop it in wet chemistry. You put the wafer in a bowl with some, I believe it was acetone or isopropyl alcohol. I think it was acetone though. And be sure to wear your personal protective equipment. This is the mask. I don't know if you want me to go over time. I know I just at some point hit the 8-minute mark, but I just want to show quickly what the mask looks like. This is the wafer I created. These are Schottky diodes, resistors, and let's see, resistors, capacitors, and Schottky diodes. There you go, there's another look. It's got the Husky over there, the UW Husky. And there's a couple other wafers to the left that I created with different patterns. Magic Leap was created at the WNF. When I was there, I worked with the research scientist that developed the first Magic Leap. She worked on the materials that went into the technology. That's really exciting. Just breezing right through here, the director of the WNF worked with the DoD to create a dragonfly that actually flies for about 10 seconds untethered, and when it's tethered it can just fly for however long you want. And the next generation of that one will be powered and controlled by lasers. Neat, right? Okay, so to conclude, photolithography enables the next generation of electronics, and it can be done by anyone who's willing to press buttons and read an instruction sheet and brave harsh chemicals like hydrogen fluoride. Okay, thanks for listening.